In the previous video, you learned about the concept of maximum power point tracking and why it is necessary in a PV system. In this video lecture, I will discuss some techniques that can be used to perform this MPPT function on a solar panel. You will learn about how these techniques are operated and how they differ from each other. All the techniques in this video can be described as indirect MPPT methods. Just to recap, the point of a maximum power point tracker is to find voltage at which the solar panel delivers the maximum power, or VMPP. If we know the VMPP, then we can use power electronics to set that voltage to our solar panel or array of solar panels. So a maximum power point tracking scheme consists of taking some sort of input and using some logic based on that input and outputting VPV, which the power electronics should apply to our PV panels. If the MPPT algorithm is good, this VPV should be as close as possible to our desired VMPP of the solar array or panel. This block diagram will be shown for every method that I share with you. There are many techniques for maximum power point tracking, but they can be divided into direct and indirect techniques. The main difference between these techniques is that direct techniques directly track the MPPT by scanning through the IV curve of the solar cell, while indirect techniques use some other input to indirectly estimate the maximum power point. This video focuses on those indirect techniques, while the direct techniques will be explored in other videos. The first such method is the constant voltage method. As the name implies, this method simply hard codes the VMPP into the system. As you saw in the last video, the MPP of a solar array can change based on temperature, shading, or other factors. However, this method considers those effects negligible and simply uses the VMPP that is measured at standard test conditions of the panels and always sets that voltage. However, a control is still needed because otherwise the panel would shift based on the load conditions. Furthermore, the voltage could start to drift away from the VMPP based on other external conditions. The constant voltage method simply takes on the current voltage of the panel and then tweaks that voltage towards the hard-coded VMPP. As you can imagine, this method is very simple, but also has drawbacks. One major drawback is that the system has to be hard-coded based on the panels. Since the MPPT logic is programmed in the power electronics components, this means that those components will only work if they are attached to specific panels with a specific VMPP. Furthermore, changes in irradiance and other conditions can cause the VMPP to shift, and this will mean that running a constant VMPP technique will result in less than ideal power output. The next technique adds a bit of complexity and is known as the fractional open voltage method. Here, we make the assumption that VMPP is a distinct fraction of the open circuit voltage of the PV panel or array. The value used here is usually between 70 to 80% of the open circuit voltage. This method is a bit more robust than the constant voltage methods, as the VOC will scale at approximately the same rate as the VMPP, thus making it more suitable for panel degradation and different illumination conditions. However, the open circuit voltage needs to be monitored periodically. This is done by disconnecting the solar panel and measuring the VOC. During these disconnections, no power can be delivered to the load, which is the main drawback to this method. So here, we need both the voltage, which is currently applied to the PV, and the open circuit voltage as an input. The algorithm will then calculate whether or not the current voltage is higher or lower than the hard-coded fraction of the open circuit voltage and change the panel voltage appropriately. Another method that is used, which is very similar to the open voltage method, is the short current pulse method. This method is unique in that it looks at the ideal current rather than an ideal voltage. Here, the maximum power point current is assumed to be around 92% of the short circuit current. Similar to the fractional voltage method, it has to periodically measure the short circuit current, ISC. And in these periodic checkups, the panels are not delivering any power. However, keep in mind that the MPPT can only really modify the applied voltage to the panels, so this method is a bit trickier than the fractional voltage method. So the input for this method is the short circuit current as well as the operating current IPV. The algorithm will check to see if the fraction of IPV to ISC is relative to the hard-coded value. Furthermore, the operating voltage VPV is necessary, and it will increase or decrease that voltage depending on the fraction of IPV to ISC. So, to recap, you learned about 3 different MPPT techniques today: the constant voltage method, fractional open current voltage method, and the short circuit current pulse method. These methods are all known as indirect methods, as they make assumptions on the maximum power point and don't actually trace the IV curve. However, these methods are fairly simple to realize electronically, so they are used in low to mid-range inverters and charge controllers. In the next video, we will look at some direct MPPT techniques that actually trace the IV and PV curves to find the maximum power point.